This is part one of I don't know how many parts videos about FPGA programming. But before I even begin talking about FPGA programming, I want to talk about how things were done before FPGAs. So just to give you a taste of what's ahead, this is called a 7-segment decoder. We have 4-bit input and a 7-segment output. This is called a 7-segment display, because it has 1, 2, 3, 4, 5, 6, 7 LEDs. And now if I change the value, so this is 0, 0, 0, 0, black is 0. If I change it to 1, it goes 1. If I change this to 1, it goes 2. And then if I change both of them, they go 3. And then 4, 5, 6, 7, and so on. So how do we go about designing such a circuit? The first step in designing a 7-segment decoder, or in fact, any circuit, is deciding what the requirements are. So, a 7-segment display is composed of, well, 7 segments. And we're going to label them A, B, C, D, E, F, G, because that's the standard way to label them. So now we need to make something called a truth table, which means we have 4 inputs. So we have input 0, 1, 2. Let's do it the other direction. 0, 1, 2, and 3. And we have 7 outputs labeled A, B, C, D, E, F, and G. So now we need to decide for every combination of the 4 inputs what the 7 outputs should be. So now we need to write them all down. So 0, I like to do it like this. They take hardly any time at all after editing. So now we need to figure out for each input combination what segments we want lit. So for 0, the value here is 0, obviously. So we want A, B, C, D, E, and F on and G off. So we go 1, 1, 1, 1, 1, 1, 0. Now for 0, 0, 1, value is 1. So we want B and C on. So we want B and C on, and the rest are 0. And then here we want A, B, G, E, D. A, B, G, E, D, and the rest are 0. And we go on for the rest of them. So 3 will be a... Now, for 9, we actually have fonts we can pick from. We can either do here, or we can do like this. Let's pick this one. So that would be... Now, that leaves us these combinations, and they represent the values 10 through 15. We don't need them, right? Because we're supposed to do something that converts the value 0 through 9 to a decimal digit. So we can just fill all of those with zeros. Cool. Truth table done. The next step is to convert this into logic gates. Now, I'm assuming you all know logic gates. If not, we have the basic ones, which are a OR, which is denoted like this. We have AND, which is denoted like this. And we have NOT, which is essentially a circle, but it's usually denoted, when it's standalone, it's denoted like this. But you can also attach a NOT to a gate. So we can do a gate that looks like this, and that is called a NOR gate, which is an OR with a NOT at the output. And actually, that's the simplest gate there is. It's the least amount of transistor, this gate. Okay, so how to convert this into this? First of all, we need a better way of denoting symbols. So we can use something called Boolean algebra. Boolean algebra looks like this. Instead of doing OR, we'll do plus. Instead of doing AND, we'll do multiplication. And instead of saying NOT, we'll do a line above the symbol. So we have Boolean algebra. Now, Boolean algebra of what? And the first thing we need to do with this table is sort of transpose it. We wrote the lines out, but what we really need are the columns. So we need all the cases under which A is 1. So we go 0 not, 1 not, 2 not, 3 not. So this gives us this one. Plus, so or, 0 not, 1, 2 not. So all of this is the expression for the A output. Now, once we wrote all of that, we can try and reduce the number of gates, because the number of gates we want here is pretty high. Each pair here is an AND gate, so that's 1, 2, 3 gates per tuple here. And we also need, each pair needs an OR gate. So we need 1, 2, 3, 4, 5, 6, 7, 8 times 3. That's 24 AND gates plus 1, 2, 3, 4, 5, 6, 7 OR gates. And this is just for this single segment. So yeah, that's not very encouraging. So how do we reduce the number of gates? Well, since this is Boolean algebra, we can use some algebraic notations. For example, we can take 0 not and then take all the elements that have that. So we do 0 not, that's 1, 2, 3, plus 1, 2, 3, plus 1, 2, 3, plus, and so on. And then try to get more common elements out. And that reduces the number of logic gates, because before each one of those required 3 AND gates, and now it just requires 2 and then 1 AND gate at the end. So this reduces the number of gates we need. There's one more optimization we can do here, and that's if we take, for example, we have 1 not, 2 not, 3 not, and we have 1 not, 2 not, 3. So we can turn that into 1 not, 2 not, 3 not plus 3. But 3 not plus 3 means it's always 1. No matter what the input 3 says, this is going to be 1. So that gets cancelled away, and we're left with 1 not, 2 not, and we eliminated 2 elements. So that's one more thing we can do. And we can do a series of those. We can use the De Morgan rules in order to reduce the overall number of gates we need in order to implement this. But as you can see, it's a lot of work. It's a tedious process. It has no organized way to carry it out. You never know whether you got the minimum set. Let's ask whether there's something smarter we can do. It turns out we can find out the minimal representation that uses nots only on the inputs and then ANDs grouped together with ORs. So the hierarchy is not and then ANDs and then ORs. We can find the minimal representation in a standard way. The way to do that is something called a Karnaugh map. So we take all of our inputs and we write them out as cells that have Hamming distance of 1. Hamming distance is the number of bits that change between two numbers. So we can go 0, 0, 0, 1. And now the next number needs to be 1 bit different than this. So it will be 1, 1, and then 1, 0. And we'll call this 3 and 2 inputs. The 1 and 0 inputs will do the same. So we'll go 0, 0, 0, 1, 1, 1, 1, 0. And now we still take the column and we write it out here. So 0, 0, 0, 0 is a 1. So that's this cell. That's a 1. And then we have a 0. So 0 and 1 go here. So that's a 0. And then the 1 isn't here, it's here because of the Hamming distance. And that's a 1. And then we go 0, 1, 1, 1. And the next line is the last one. 1, 1. And the rest are zeros. The next thing we need to do is we need to find a rectangle that each side is a power of 2 that covers only ones. And we want to make it as large as possible. So if we circle a single one, that satisfies, but we want it the largest that there is. So we can go this. It's a 2 on 2 rectangle. That's fine. And if we look at this rectangle, what we see is that what characterizes it is for input 0, there's nothing we can say about this rectangle. But for input 1, we saw that it's all ones, always. And the same goes here. If for input 3, it's all zeros. So this rectangle is represented by the expression 1, 3, naught. And now these ones are covered. We have an expression that generates them. So we can take them out of the equation. But there are still ones we haven't covered. So we can do this expression. This expression, 0 is 1. So we can write 0. Let's do that in sequence. And 1 is either 0 or 1. But 2 and 3 are 1 and 0. So that's this rectangle. We also have this rectangle, which is 1 is always 0. And then we have 2, naught, 3. And last we have this one. And it seems like it's all along, which means we'll have to specify all 4 inputs. But actually, if you look at this row, it's a Hamming distance of 1 from this row. And this column is a Hamming distance of 1 from this column. So we can actually extend the rectangle either to the left to this one or to the bottom to this one. So let's do the bottom one. So this coverage. And here we have 0, naught, 1, naught, and 2, naught. So these expressions give us A. And now we can do the same thing for the rest of them. And we will get some expression that covers all of the 7-segment display and gives all LEDs off when we're outside the range of 0 to 9. And now we can take logic gate shapes. I'm using the 7-4 series. The 7-4 series generally looks like this. They have 2 inputs and an output, and altogether they have 4 binary gates. We can generally say that each 4 logic gates are one shape, except for the NOTs. Since the NOTs are unary gates, there are 6 gates in a chip. So we can lay it out and make it work, and it will be huge. But wait a minute, we've already seen it in action, and well, it's not exactly nice. It's not huge. It's just 7 chips, which means at most, this is 28 logic gates. How did I do that? Well, I'll give you 2 hints. The first hint is what happens when I want to encode a 9. You'll notice that I specifically get the version without the leg. Why? Because it would require more logic gates in order to get the version with the leg, so I chose the one without. Which pretty much begins to tell you what I'm doing here. I'm adapting the requirements. I have some leeway within the requirements, and I'm using the leeway in order to take something that satisfies the requirements, however, does so in a way that it uses less gates. The other thing to notice is what happens when I input an illegal value. So if I put in some other value, I get random stuff. It might not even be a legal-looking digit. What's going on here? What's going on here is that I had no requirement for the numbers above 10. So I wrote 0, but I didn't need to write 0. I could also do something that will minimize my design. Let's see how I chose that. So if we look at the Karnaugh map we did, the Karnaugh map, the bigger the area I was using, the more inputs could be either 1 or 0 and wouldn't appear in the expression. So the bigger the rectangle, the better. But otherwise, I needed to cover all the ones in the design. But these zeros needn't be zeros. They can be either 0 or 1. So I can repeat the Karnaugh map for A. And we can repeat writing the values. And then everything else is undefined, so I'll write in x's. Now here's the thing about x's. I am allowed to expand a rectangle to cover an x. This is a 0. I'm allowed to expand a rectangle to cover an x, but I'm not required to cover all of the x's. So these give me better leeway in designing my logic. So now if I write out the result, this used to be these 4, but now they don't need to be these 4. I can expand them down, and if I do so, the requirement these spell out is 1. Input 1 must be on. All the other inputs are don't care. Which makes sense because this covers half the table. And if I do this, so this is this. And now I can also do this, which translates to 3, which leaves me this one and this one. So for this one, I can pick this rectangle, and that would be 0, 2. And for this one, I can cover it in the same one as this. So that would be 0, 0, 2, 0. Now here's the thing. Assuming I already have all of the inputs as both straight and inverted, so I don't count the knots. But if I don't count them, what I have here is 1, 2, 3, 4, 5, 6, 7 ends, and 1, 2, 3 ors. So 7 ends and 3 ors. Whereas here I have 2 ends and again, and still 3 ORs. So you can see that there's a huge saving on logic gates by allowing undefined values. And all I needed to do for the 9 is put an X here. Say, I don't care for input D, just put an X where the 9 is, and then I don't care if it's on and off. If it turns out it's better to do it off, then fine, I leave it off. So this allows me to implement a 7-segment decoder with 7 gates, which actually, if we look at the map I made when I created it, we can see that I have one OR gate that is unoccupied and one AND gate that is unoccupied. So I have, on average, half a chip that is actually available. But either way, we have a working 7-segment decoder here. But there's another way to do that. That other way, and you can see it's much, much simpler, is to use a ROM chip. So this is the AT28C256. It's a 32 kilobyte ROM, which means it has 15 address lines as inputs and 8 data bits as output. 7 of those data bits are hooked up to the 7-segment display. You see, this is a much, much simpler setup. And now I can do the same thing. This is 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the rest are 0. All of the high values are 0. So how did I go on creating this? Essentially, in order to create this, in order to create the programming for the ROM, all we need to do is take the truth table as we used it. We treat every one of those as a bit programmed in the ROM, which means all we need to do is convert this to hexadecimal, store it in a file, burn it to the ROM, and place the ROM back here. Now, the 16 values cover just 16 bytes of the 32,000 bytes we have here, so we have plenty of room. So what I did is essentially almost all the lines here that you see here as black are, except for 2, they are address lines that I tied low so that they wouldn't flicker. But we have so much space, I can get creative. So 9 is like this, but I used 2 bits of the address to specify different fonts. So if I just switch to a different font, we get the 9 with the leg like we wanted. And now, if we take, for example, this is 10, which currently is just off, but if I add this leg, now we have hexadecimal digits here. So this is A, B, C, D, F, and E. But, you know, there's something strange about C. Because it can be big, but it can also be smaller. So I can even do that by setting the leg. So I have plenty of room. Now, I think everyone can see that programming a circuit using ROMs is simpler, it's much more straightforward, and it definitely cleaner. But it even requires less circuits. So the obvious question is, are there any downsides? And the answer is, oh boy, are there downsides. Let's begin with the cost. Each one of those logic chips costs $50 if you buy it with a single chip at a time. This means that the entire logic here costs $3.50. The 32 kilobyte ROM costs over $11. Even if I downgraded the ROM to something that is smaller, the lowest I can go is $5. So this thing is way, way more expensive. Well, none of them are actually expensive, but you get the drift than this. The other aspect of this, and the reason why it's expensive, obviously this is an overkill for this circuit, right? We have 32 kilobytes here. We're using about 16. So 16 bytes, not kilobytes. So obviously there's plenty of room here, but we can't really use that room because we've already used 7 of the 8 output bits. So we could theoretically do another circuit that maps. We have 15 inputs and we're using 4, so 11 bits to 1 bit. But I'm hard-pressed to understand why that would be useful to anyone. The other downside is the amount of transistors here. Now, if you think about it, this makes sense because here the logic is implemented with this rat nest of wiring. Whereas here, everything is laid out and programmable, but there's a logic that needs to do the address resolution, and that logic requires a lot of transistors. Another downside of the ROM method is something called hazards, which I have not talked about. Very briefly, hazards is when you have a single bit change, for example, from here to here, that goes from 1 to 1, but because it's covered by different logic sets, there's an interim 0, and that can cause problems. And the problem with hazards with ROM is that they're unanalyzable. You cannot analyze the circuit to understand when hazards happen. And the other problem is that they're unsolvable. There's nothing you can do in order to solve them. And both are not correct for discrete logic. You can both analyze it for hazards and solve them by adding more gates in discrete logic. So this has a huge amount of downsides. But it has one huge upside, which is the person generating the chip doesn't need to know what logic I intend to implement using it. And I'm obviously hinting to FPGA programming here, but we're going to talk about that in the next video.